Hello and welcome to today's video. This video is going to be rather short. Basically, all we do is define a name for things that we have already worked with. You will remember we have introduced Taylor polynomials as a means of approximating functions locally through polynomials of a given order. And when we talked about approximation, we have already dealt with the question of how good this approximation is going to get if we allow for arbitrarily high values of n, arbitrarily high degrees. So formally, we've already used series here. And well, the title of this section is Taylor series. Basically, we're just going to define what a Taylor series is. So this is called Taylor series, and it consists of a definition and a short remark. The definition just summarizes what we have already done. So as usual, when we talk about Taylor approximation, we need an open interval. So let I be a subset of R. That is an open interval. Let X star be a point in that interval. And let F be a function on that interval that is arbitrarily often continuously differentiable. And just as a quick remark, what that means is, so there's a convenient notation for that. What that means is F is contained in C infinity of I. Remember, Ck of I are the k times continuously differentiable functions on I. So arbitrarily often, that is denoted as C infinity. And then we can define a Taylor series, and that is simply written as Tf. We skip the index here. That would usually indicate the degree, but the rest is the same, and that is the Taylor series. That's defined as the sum from 0 to infinity of the kth order derivative of A at x star over k factorial times x minus x star to the power of k. So the Taylor polynomials, but with n to infinity. And that is called the Taylor series. Of f at x star. So as I said, we have worked with those already, so that's not a big surprise, hopefully. Two things that we have already seen, just as a quick remark. Of course, you can write down a Taylor series for every function that is infinitely often continuously differentiable, but that does not mean that the Taylor series converges. It will converge at x star, obviously, because all summands of the Taylor series will be 0 at that point, apart maybe from the actual function value, but that's a finite number, so that's going to converge. But it might not converge anywhere else. So that's the first point of our remark here. Saying the Taylor series of a function might not converge at all at points other than x equals x star. And the second remark is, even if it does converge, that does not necessarily mean it converges against the original function. So it might converge, but the value, at least for certain x's, might not be the same as the value of the function that we used to get that Taylor series. So second remark, even if the Taylor series of a function f converges for some value of x in I, it might not converge to f of x. So please be careful when working with Taylor series. In many cases this works very well, but there are quite a couple of cases where the Taylor series is either non-convergent, or even worse, it is convergent, but it gives the wrong value. It does not give the function value that you actually want. And of course, if you're really working with Taylor series, you have to be sure about convergence and convergence towards the function that you're working with. Otherwise, the results will be horribly wrong and you might not even notice. Okay, so as a word of warning about Taylor series, and as I said, we have already seen examples of Taylor series when we talked about the Taylor approximation. So if you want examples, just go back to the previous videos where you can see these. This concludes our investigation into Taylor series for now. In the upcoming videos, we'll talk about integration as a very important point of calculus. So we'll develop an integral, and we'll also talk about integration rules and things like that. As usual, I hope I see you then.